Beam. Beam is a straight bar that primarily subjected to transverse loads. The shape of the beam is described by the transverse displacement and its rotations, or we can say slopes of the beam. Hence, the transverse displacements and slopes of at each end of the beam are treated as unknown degrees of freedoms. So, before going to discuss that one, first try to understand the basic, recollect the basic concepts of this beam, calculations related to how to find out the bending moment and shear forces of the beam. From the mechanics of solids, we can recollect it. So, consider the one beam element. This is the beam element here. We can see that beam element has length L. This is the beam element of length L here. So, for understanding purpose, under equilibrium conditions, we may say that force under equilibrium condition. So, for the analysis, first we consider one small element ABCD. This element we consider for the analysis under equilibrium conditions. It is subjected to UDL load, small w. Suppose the force is acting one side is force upward Fe, vertical force in this direction and downward direction in this direction. It has some displacement dx for this element. So similarly, moment is in this side is m and other side is m plus dm because of this change in length of this element. Under equilibrium equations, we can say that force, vertical forces is equal to 0. Sigma f of y is equal to 0. So vertical force, what are the vertical forces? Fe in this side and here the Fe and minus f plus df, this one. So minus w into dx, this downward force because of this UDL load is converted into point load. We can say the shear forces. Load into displacement we gives the shear force. This is under equilibrium conditions. So in this equation, under equilibrium conditions, we can find out w is equal to dFe by dx, because and this Fe and the Fe can cancel, and finally we can w mean UDL load is equal to dFv, vertical force be divided by dx under equilibrium conditions. This is similarly moment under equilibrium, and moment equilibrium, here we can say that m2 about this m1 is equal to 0. So here is about node 2, we consider the m2 means moment taken, consider about node 2. So m2 is equal to 0. So minus from here to here distance is Fe into dx, this distance into this one, and dm because this moment of this particular element, plus w into dx by d, because from here to here distance, shear force is w into dx, and distance from here to this center point to dx by 2. So this is the moment equilibrium equation. From this moment equilibrium equations, we can say that force in vertical direction is equal to dm by dx. So from this shear force and load, UDL load acting on this element, we can find out these relations. W is equal to d square m by dx square, because this one is a relation between these two. W is equal to d square m by dx square. Also we need to substitute in this equation in this. Similarly, from this bending moment equation or simple theory of simple bending moment equation, we can say m by I is equal to E by R is equal to phi z. So from this equation we can say that this is the, suppose when beam is subjected to loads, it may bend like this. So this is the bending. So it has a curvature has center point is this one is C. So from this distance is R. So this ds is equal to r d pi, because we can assume dx is equal to ds. So 1 by r is equal to, from this equation 1 by r is equal to, we can write it as d pi by dx from this diagram when it is subjected to loads or bending. So we know that this equation tan pi dy by dx. So pi is equal to, we can simply, for the small angles, pi is equal to dy by dx from this diagram. So we can say that dy by dx is equal to d square y by dx square, because we know that 1 by r is equal to d pi by dx. So we can differentiate with respect to pi. D pi by dx is equal to d square y by dx square. This equation, we have to differentiate this equation, we will get this one. So 1 by r is equal to, we can say that d square y by dx square. This one is 1 by r. This is a relation between these two. This is okay, this equation. So 1 by r is equal to d square y by dx square. This is the equation. From the bending moment equation, we know that this is the bending moment equation. M by I is equal to E by R. M by I is equal to E by R. So M by 1 by R is equal to M by A. So we can equating these two. M by A is equal to d square by dx square. From this equation, we can write it as, this is the bending moment equation. From this, from the basics already we derived this one. W is equal to d square M by dx square. In the previous slides already we derived the relation between the UDL load and its bending moment. So we substitute in this equation. So substitute in this equation, W is equal to d square by dx square into A into d square y by dx square. So finally we can say that A d square y by d to the power of 4 y by dx to the power of 4 is equal to 0. This is the equation of motion. So in this we consider here as the two noded beam element. At each node 2 degrees of freedom. One is the transfer displacements, another one is the slope. So there are the 4 unknown degrees of freedom. For in this case, 4 nodal displacements we assume as a cubic displacement model. Cubic displacement model. This is the cubic displacement model equation 1. In this case, this is the displacement equation, one dimensional displacement equation. So its slope means derivative of its displacement, dy by dx is equal to, this is equation, another equation 2, slope dy by dx. So suppose this one is node 1, node 2, its length is L, beam element. It has and y1 at node 2, displacement at y2 at node 2. Here at node 1 theta 1, node 2 theta 2. So these are the 4 degrees of freedom. So boundary conditions, we know that at node 1 x equal to 0, because the axis varies from 0 to L, from here to, suppose this one external, the axis varies from 0 to L. At node 1, what we can say, that x is equal to 0. Though x is equal to 0, boundary conditions can substitute in equation 1 and 2. Finally you will get the values. So similarly at node 2, x equal to L. So substitute this x is equal to L value at node 2 conditions. So y is equal to y2, dy by dx is equal to theta 2. Now substitute these values in. So at node 1 x is equal to 0, we substitute means y1 is equal to a, because remaining all the terms will be appears, x term is there, because x is equal to 0, we can say that y1 is equal to a1. Similarly y theta 2 is equal to this is equation 3, we will get by substituting at node 1 boundary conditions. Similarly substitute node 2 boundary conditions in equation 1 and equation 2. These two will get, these are the equation 4s. From the equation 3 and 4, already there are the 4 unknowns a1, a2, a3, a4. Here a1 is equal to y1, we can directly say that a2 is equal to theta 1. Now we have to find out the a3 and a4. a3 and a4 are the constants. a1, a2 constants already we directly we will get it. So a3 and a4, by substituting these values in and simplifying, finally we have to find out the a3 and a4 value. After finding the a1, a2, a3, a4 values, substitute in equation 1 and equation 1. Now we will get that equation will what as 4. So this equation is after finding the its a1, a2, a3, a4 values. So some in terms of its parameters y1 and some parameters into theta 1, y2, theta 2. Here this simplifying this equation. So y is equal to n1 y1, n2 theta 1, n3 y2, n4 theta 2. This is equation 5. This equation shows that what is n1, n2, n3, n4 are n1, n2, n3, n4 are the shape functions of this beam element. The shape functions n1 is equal to we can write it as n1 is equal to this value 2x square minus 3lx square plus l cube divided by l3 n1, like that n2, n3, n4. Now we can write it, this equation is this one, this is the same equation, we can write it is in terms of its vector forms. This is equation 6, the transpose matrix. So n y is equal to n cube. What is n? N is the matrix of n1, n2, n3, n4 shape functions of this beam element. That is q. Q is equal to y1 theta 1, y2 theta 2. So n1 is equal to, already we derived, n1 is equal to this equation, n2, n3, n4, n2, n1, n2, n3, n4 are the shape functions of this beam element. This beam elements also, there is another name for this beam element, that is called Hermite shape function. These shape functions, these n1, n2, n3, 4s are also called as Hermite shape functions. Hermite shape functions. So how this shape functions varies along its length of the beam. Now n1 is already in terms of 1 minus 3x square, 3 by x, 3 into x by l whole square plus 2 into x by l whole cube. How this n1 varies along its length of the beam, it shows in this figure 1. How the shape function, one function varies by varying its x value. X is equal to 0 to 1. So maximum at this node one side. Similarly n2, x we can varies from x is varies from 0 to l. We can develop a graph. Similarly n3 also and n4. These figures represents the how the shape functions are varying along its length of the beam. So the n1, n2, n3, n4s are the shape functions. Hermite shape functions are beam shape functions. These are the important shape functions.